Hello, this is a tutorial on converting fixed point value to base 10, specifically only using bit shift and adding. The prerequisite knowledge required for this video is that you are familiar with binary numbers, right shifting binary numbers, multiplying binary numbers, as well as being able to do bitwise AND. So what are fixed point values? Fixed point values are a way of representing non-integer values as integers. So if, for example, we have a number like square root 3, which roughly equals 1.73, we can write that in its binary representation as 1.10111011, so on and so forth. And if we were to take the upper 8 bits of the binary representation and put it into a number, and what I've done here is I've also looked at the 9th bit. The 9th bit here happens to be a 1, and because it's a 1, what I've done is I've rounded up the 8 bit, and that gives me this number here. This number is our fixed point value. So our fixed point value is equal to our square root 3, so 1.73, multiplied by 2 to the power of 7, as we have 7 bits below the radix point in this fixed point value, and this fixed point value just so happens to be the integer 222. So to generalize, we can put together this equation. So the fixed point number is equal to the actual value multiplied by 2 to the power of r, where r represents the number of bits below the radix point. Now, using this equation, we can easily turn any value into fixed point notation. But how do we now convert a fixed point number back into its original base 10 form? So let's say you have a fixed point value stored in a CPU and you want to display that value. Well, how do you do that? Well, we could rearrange the equation. Since we know b2 and we know r, we can rearrange the equation for v, giving us v equals b2 over r, 2 to the power of r. And to calculate this on a simple CPU, we could naively take our value and right shift it r times. So if we take the fixed point value for square root 3 and right shift it 7 times, we get 1. Now 1 is very different from 1.73. So what went wrong? Well, right shifting gets rid of all of the bits that are below the radix point, since they all get shifted out. And what this means is we end up with 1.73 minus 0.73, so effectively getting rid of everything below the radix point, which just gives us 1. So how do we keep the numbers, or at least some of the numbers, below the radix point? So the trick is, we do not want v. Instead, we want v multiplied by 10 to the power of capital R, where capital R is the desired number of decimal places in our result. If we plug that into our equation from before, then we have v times 10 to the power of capital R equals b2 multiplied by 10 to the power of R divided by 2 to the power of R. And this simplifies to this. All I have done here is I have divided the top and bottom of the equation by 2 to the power of capital R. So if we take this equation and insert the fixed point value that we had before and the radix, bits below the radix that we had before, which is 7, and this will set capital R to equal 2. So this should give us 2 decimal places. So if we substitute those numbers into our equation, we get our fixed point value, which is the integer 222, multiplied by 5 squared divided by 2 to the power of 5. If you put that into your calculator, you will get 173 and some numbers below the decimal place. So this has given us an integer. If we just concentrate on the integer portion, this has given us the value that we want to 2 decimal places. So how would a simple 8-bit CPU perform this calculation? The value needs to be right shifted 5 times and it must be multiplied by 5 twice. So a naive approach would be to right shift first and then multiply after. So if we start with our fixed point value, which is 222, and we right shift it 5 times, we get the number 6. Then if we take 6 and multiply it by 5 twice, then we get 150. So this means our final answer is 150. Now 150 is quite different to 173. It's close and the error is a bit over 10%, but it's not very accurate. The error is large because many of the bits in our fixed point value were shifted out when right shifting. So how could we reduce this error? We could potentially multiply by 5 before we fully right shift the value. So again, the value needs to be right shifted 5 times and it must be multiplied by 5 twice. And these operations can happen in any order as multiplication and division are commutative. So if we start with 222, we could either first multiply by 5 or we could right shift. If we multiply this value by 5, however, the answer would be much larger than 255, which is the largest value that we can store within 8 bits. So this would cause us to lose some of the bits in B, so we want to right shift first. So we right shift 222 to give us 111. If we multiply 111 by 5, the result will be larger than 8 bits, so we must right shift it again. So 111 right shifted again gives us 55. Again, 55 multiplied by 5 would be larger than 8 bits, so we must right shift one more time, giving us 27. The 27 that we now have can be multiplied by 5 without losing any bits. So 27 times 5 gives us 135. After multiplying by 5, we must right shift at least twice before multiplying by 5 once again. So now we can take the 135 and right shift it twice, which gives us 33. Now we can multiply by 5 without losing any bits. And this is the final multiplication by 5. So 33 multiplied by 5 gives us 165. So the final answer is 165. 165 roughly equals 173 with an error of just under 5%. This is still not perfect as we still lost a couple bits by right shifting, but it's much more accurate than the previous method. However, can we do even better? We could expand the number of bits from 8 to 16. This would be very accurate as no bits would need to be shifted out, but doubling the word size would significantly slow down the program on an 8-bit CPU. So is there a compromise that we could use to keep the value at 8 bits? We could simply round the number up whenever we shift out a bit. So if we start with 222 again, we start by right shifting. This is the exact same steps as the previous method. So we right shift 222 to give us 111. And now since 111 is odd, on our next right shift, we must add 1 to round the value up. So 111 right shifted gives us 55, and then plus 1 gives us 56. We then right shift the 56 once more to give us 28. Now we take the 28 and multiply by 5. This gives us 140. And now we must right shift twice since we have just multiplied by 5. Now the 140 can be right shifted twice. The first time we right shift it, it gives us 70, which is an even number, and 140 is also an even number, so that means we do not have to add 1 in either case. So the result of right shifting it twice is simply 35. Now we can multiply by 5, which is our final multiplication. So 35 multiplied by 5 gives us 175. So our final answer is 175. 175 definitely is very close to the target value of 173, with an error of only just over 1%. However, this is still not perfect as we had to round the value, but is much more accurate than the previous method. Can we do better still? We could keep track of the bits that get shifted out. The maximum number of right shifts in a row is 3, so this means a maximum of 3 bits could end up being shifted out. We could keep track of these bits using another value, BO, which represents the bits that have been shifted out. This will make the result perfect with 0 error, but at the cost of extra complexity. So when we right shift the main value, we must also right shift BO, and we want to add 5 to BO when we right shift an odd number. The reason we want to add 5 is so that we can add BO to our main value when we multiply by 5. Then, when we multiply by 5, we right shift BO and then add it to the main value. BO then becomes BO and with 1. So what that does is BO becomes the lowest bit of BO. That bit is the bit that gets shifted out when it is right shifted. This keeps track of all of the bits which get shifted out and allows us to correct the main value when we multiply by 5. So again, we start with 222, which is our fixed point value, and BO starts as 0. We start by right shifting, and this is the exact same steps as previous method. We right shift 222 to give us 111. Now, because 111 is odd, the next time we right shift, we must add 5 to BO. So 111 right shifted gives us 55, and BO is right shifted, which gives us 0, and then we add 5, which gives us 5. Now 55 is odd again, so we must repeat the same steps. So 55 is right shifted into 27, then B0, which is 5, gets right shifted to give us 2, and that is then added to 5, which gives us 7. The number 27 can now be multiplied by 5. So we multiply it by 5 and then add it to BO right shifted once. So 27 times 5 equals 135, and BO right shifted once equals 3, which then can be added together to give 138. Then we AND BO with 1, so 7 ANDed with 1, which gives us 1, so BO now equals 1. After multiplying by 5, we must right shift again at least twice. Now we take the 138 and right shift it. This gives us 69. We also right shift BO, which is 1. This gives us 0. Now, as 69 is odd, we must add 5 to BO next time we right shift. So 69 right shifted once gives us 34, and BO, which is 0, right shifted once gives us 0, added to 5 gives us 5. We now do the final multiplication by 5, so 34 multiplied by 5 plus BO right shifted once, so 34 multiplied by 5 gives us 170, and BO right shifted once gives us 2, so them added together gives us 172. Then BO is ANDed with 1 to give us 1. We have now finished multiplying by 5 and dividing by 2, so we can take the remaining value in BO, and if this value is more than 0, then we should add 1 to our main value to round it up. So we have 172 plus 1, since B0 is more than 0, to give us 173. So the final answer is 173, and 173 is exactly equal to the target value of 173. This gives us an error of 0%. This method is the most accurate, but it is the most expensive computationally. The best method is the simplest one, which is acceptably accurate for the particular situation. And before I finish, I will show a couple of programs which implement this algorithm. So this first program is written in B code and does exactly what we just did in method 4. You can pause the video to look at this code if you wish. And this program is exactly the same, except it's written in URCL code. The program was too long to fit on one slide, so I've split it into two sections. The left section is the top part of the program, and the right section is the bottom part of the program. Again, feel free to pause the video if you want to look at the code. That's all I wanted to cover in this tutorial. Thanks for watching, and cheerio!